Hi everybody! In this lecture we're going to pick up where we left off last lecture with differentiation. So on this slide I've just put a couple of the main messages from the previous lecture. We said what it meant to say that a function f was differentiable at a point c in its domain. We gave two characterizations for that in terms of something called the difference quotient. So here, the difference quotient we started with was the limit as h goes to 0 of the quantity f of c plus h minus f of c over h. And then towards the end of the previous lecture, we said that that's equivalent to saying the limit as the input x approaches the point c in the domain of f of x minus f of c all over x minus c. These compute the same quantity. If this limit exists, it's the derivative of f at c. That quantity is a number, and what that number tells you is the slope of the line which lies tangent to the graph of y equals f of x at the point c f of c. Notice both of these difference quotients are rise over run. It's a change in outputs divided by a change in inputs. So this, of course, is what we call the difference quotient, and rise over run we associate to this notion of slope. Today we're going to look at a lot more rules. We saw one rule last time because it was so useful. We have, these kinds of quantities all the time, and that was the power rule. So if we have a function that can be written as f of x equals x raised to some power p, then the derivative of that function is p x to the p minus 1. Before we proceed to look at more techniques of differentiation, more shortcuts that allow us to compute a derivative immediately without needing to compute a difference quotient, let's actually first look at a theorem. This theorem says if f is differentiable at a point c in its domain, then f is continuous at c. In other words, differentiability implies continuity. The converse is not true. So being continuous does not imply being differentiable. Differentiability is somehow a stronger, more exclusive notion than that of continuity. Okay, let's go through the proof. We want to prove that the limit of f of x as x approaches c in the domain goes to f of c. We're going to show that this holds using the difference quotient. So since f prime of c exists, our hypothesis here is that f is differentiable at c. We know that the limit as h goes to 0 of f of c plus h minus f of c all over h exists. That's a finite number. It's the slope of the tangent line. It's whatever the number f prime of c is. Now we're going to do something that feels a lot like working backwards in my opinion. Using the algebraic limit theorem for functional limits, I'm going to take the number 0 and say that 0 is equal to f prime of c times 0. That's just a fact. And now each of the quantities in this product I can write as a limit which exists. So f prime of c is the limit as h goes to 0 of f of c plus h minus f of c all over h. And then 0, it's kind of a funny way to write the number 0, but 0 we'll think of as the limit as h goes to 0 of h. So this proof is sort of funny. It's the kind of thing you play around with it until you figure out how it works, because I don't think I would ever jump off from this point. It just feels so backwards to write the number 0 in this way. Since these limits both individually exist, I'm going to merge them into one single limit using the algebraic limit theorem. So we can say that 0 is now going to be equal to the limit as h goes to 0 of f of c plus h minus f of c all over h times h. The h's cancel, and we're left with the limit as h goes to 0 of f of c plus h minus f of c. Notice f of c is just a number. That's just the output when we plug c in. So if this limit exists as h goes to 0, that means that the first term, f of c plus h, must go to that number f of c. Hence, the limit as h goes to 0 of f of c plus h equals f of c. And that's exactly the notion of continuity. As we approach c in the domain, the outputs approach f of c. That's the definition of continuity. So f is continuous at c. Our next theorem is combinations of differentiable functions. This says that the derivative of a sum is the sum of the derivatives, assuming that both of those functions are differentiable. So f plus g prime is f prime plus g prime. The second one says that you can pull a constant out in front. So if you take a function and scale it by k and then compute the derivative, that's the same thing as k times the derivative f prime. The third and fourth one have kind of strange forms. So for the third one, the derivative of a product is a sum. We can say f times g prime is f prime g plus f times g prime. This is called the product rule. In some sources, it's called the Leibniz rule. And then the fourth one, if g of c is not equal to 0, then f divided by g prime is the famous quotient rule. So low d high minus high d low over low low. The fourth one can actually be derived from the third one by computing the derivative of 1 over g and then viewing f divided by g as f times 1 over g. So let's just sketch the idea of how you would prove the third one. We want to show that the difference quotient of the function f times g has a limit which looks like f prime g plus fg prime. So here's the numerator of the difference quotient we would need to work with. It would be f of c plus h times g of c plus h minus f of c g of c. What I'm going to do is introduce in like an intermediary term. I've got to cancel that term out so that I don't actually change this expression, but I want to step from the first term to the second term through a sort of mutual friend. So here's my first term. Now what I'm going to do is keep g of c plus h like it is, but change the first one to f of c. So from this term, let's subtract f of c times g of c plus h. But I got to add that back so that I don't actually change anything. And now let me take off f of c, g of c. The idea here is that when you look at these first two, the g of c plus h they have in common, so you could factor that out. And then f of c plus h minus f of c is the kind of expression you would want to see if you were, say, computing the derivative of f. Similarly, for the second one, the f of c you could factor out front, and g of c plus h minus g of c is the kind of numerator you would get in a difference quotient for g. Now the idea is as h goes to 0, if I pull that g of c plus h out and let h go to 0, that's just going to go to g of c, but then f of c plus h minus f of c divided by h will go to f prime at c times g of c, plus pull f of c out, that's actually just a number, let h go to 0, g of c plus h minus g of c divided by h is g prime at c. So this setup would lead to a proof of the product rule. Okay, let's see how to use those results from the previous slide in order to start computing the derivative of functions which are built out of other functions in such a way that allows us to avoid using the limit of the difference quotient each time. So here's an example of a polynomial. And what you'll see is the methodology we use to compute the derivative of this polynomial at the point 5 would work for any polynomial. So just based on the first two rules from the previous slide, the fact that the derivative of a sum is the sum of the derivatives, and that scalar multiple rule, those two rules together with the power rule allow you to differentiate any polynomial. Okay, so in particular, we have f of x equals 3x squared plus x minus 7. This is the sum of three terms. So let me label the first term 3x squared as 1, the second term x we'll call term 2, and then the third term is just this minus 7. We'll do each of these derivatives individually, but once you've gone through this a couple of times, you'll see that you don't have to attack this piece by piece. You can pretty much eyeball these and compute the derivative right away. Okay, so f prime of 5 is going to be the sum of the derivative of 3x squared at x equals 5, the derivative of y equals x at x equals 5, and the derivative of y equals negative 7 at x equals 5. 3x squared is 3 times x squared. So using the fact that scalars pull out, together with the power rule, we can say that the derivative of 3x squared at x equals 5 is 3 times 2, 5 to the 2 minus 1. Or in other words, 3 times 10 is 30. To differentiate y equals x, we can again use the power rule. X is x to the 1. So with the power rule, the derivative at 5 is going to be 1 times 5 to the 0, which is 1. If you don't like using the power rule in that setting, there's no reason why you can't. But if you don't like it, you can also just compute the derivative of this using the limit of the difference quotient. Let me do the second style. We want to compute the limit as x approaches 5 of f of x minus f of 5 over x minus 5. But that's equal to the limit as x approaches 5 of x minus 5 over x minus 5, which is 1. And then lastly, the derivative of any constant function, like y equals negative 7, is just 0. And again, for that, you can compute the limit of the difference quotient in a straightforward manner. If we take the limit as x approaches 5 of f of x minus f of 5 over x minus 5, where our function sends everything to negative 7, then that's going to be the limit as x approaches 5 of negative 7 minus negative 7 all over x minus 5. The numerator is always 0, whereas the denominator is approaching 0. However, 0 divided by a non-zero number is 0, so this limit is 0. Now that we've computed these three derivatives individually, we can add them together in order to get f prime at 5. We find that f prime at 5 is 30 plus 1 plus 0, which is 31. So far in the last lecture and in this one, every time we've computed the derivative, we've anchored it at a specific point. So we've said, given some point c in the domain of our function, f prime of c is a number, and that number is the slope of the tangent line to the curve y equals f of x at the point c, f of c. But this process of going from a point in the domain to the number which we associate to the slope of the tangent line is a mapping. Thus, we can view this action of differentiating as creating a new function which we denote f prime, sending points of the domain to f prime at x. So the idea is, given some point c in the domain, f prime of c is a number, assuming it exists. From this, we build up a function f prime that takes an input, what we typically have called c, and returns the number f prime of c as output. It's a small distinction, actually. F prime of x is now going to be a function of x. So f prime of c, given a number c was a number, f prime of x is going to look more like a function. Just a quick remark on notation. I like prime notation, so I often write f prime of x. This is Lagrange's notation. df dx or ddx of f of x are also common. This notation is called Leibniz notation. Usually I like to denote my functions as f of x, but if you were calling your function y equals x squared or something like that, you might write y prime of x, dy dx, etc. Okay, let's look at a couple examples. We want to find f prime of x if f of x equals 3. In other words, what we're going to return is a function where if you plugged any value from the domain into the function, what you would get out of that is the value of the derivative at that point. We just said in our previous example that if you have a constant function, the derivative is 0. So f prime of c equals 0 for all c for a constant function. Since, given any point from the domain, the derivative is 0 at that point, f prime is the function f prime of x equals 0. You plug in x, you get out 0. Okay, next let's look at the function f of x equals 5 times the square root of x. To differentiate this, it might be easier to say 5 times x to the 1/2 power so that we can use the power rule. For any x, where here I'm not going to specify a value, we would use the power rule to say that f prime of x is 5 times 1/2 x to the negative 1/2. If you want to put that back in root form, that would be 5 over twice the square root of x. Now here, the point in the domain was not specified. This is a function. So if I want to know what the value f prime of 1 is, then I can just plug 1 into this and get f prime of 1 is 5/2. Here's the graph of this function. Now using the form of the tangent line that we looked at last lecture, I can graph the tangent line, where here I knew immediately that the slope was 5/2. If I'm more interested in the tangent line at 4 f of 4, then I know the slope is 5/4, so I can quickly put in the formula for the tangent line at 4 f of 4. What the previous two examples illustrated is that finding the function f prime of x essentially amounts to finding the derivative in the usual way, where we're not specifying a point in the domain. So the general approach using the limit definition would be to say that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h, where here we don't choose a value for x. Alternatively, if a shortcut applies, then you can apply the shortcut to the function, again without specifying a specific point in the domain. So let's do that for this example. Suppose f of x is the rational function x squared divided by x plus 10. We could set up a difference quotient for this, but I'm going to compute the derivative using the quotient rule. The quotient rule is low d high minus high d low over low low. So here, high is the numerator, x squared. Low is the denominator, x plus 10. D high is 2x. So that's d high is the derivative of the numerator, whereas d low is 1. So there are a lot of pieces to the quotient rule, but it's not too bad once you put it all together. So low d high minus high d low over low low in this instance is going to be low d high, so x plus 10 times 2x, minus high d low, so minus x squared times 1, all over low low, which just means the denominator squared, so all over x plus 10 squared. Sometimes this simplifies, sometimes it doesn't. Let's see here, I'm going to get 2x squared plus 20x minus x squared all over x plus 10 squared. You usually don't get much out of expanding the denominator. In fact, later if you're looking for vertical asymptotes or something like that, it's preferable to keep the denominator factored. So the most I'm going to do to this is write it as x squared plus 20x divided by x plus 10 squared. Again, now given any point in the domain, I can immediately compute the slope of the tangent line. So for example, f prime of 0 would be 0 divided by 100. So f prime of 0 is 0, which means the slope of the tangent line is 0 at x equals 0. So the tangent line is flat. On the other hand, f prime of 1 would be 1 plus 20 divided by 11 squared, so 21 over 121, etc. We've looked at ways to combine differentiable functions through multiplication by a constant, addition, subtraction, multiplication, division. Here's another way to combine differentiable functions, and that's through composition. So this theorem is called the chain rule, and it says let f be a function from some domain a to the real numbers, and let g be a function from some domain b to the real numbers in such a way that the composition g of f is well defined. In other words, f of a is part of the domain of g, so that if I take some point c from a and plug it into f, I go to some point f of c, which I can then plug into g. So this first sentence is just saying, suppose the composition g of f is a defined composition. Okay, so I've written this as g of f using that kind of circular notation, but of course you could also write this as g parentheses f of x. And I like this notation sometimes more because it really emphasizes that there's an outside function, here g, and an inside function, f. So the idea is f is kind of sitting inside. So the derivative of g of f of x at a point c, sorry, I have x on the left-hand side here. I'll fix that in a minute. That should be c. But g of f prime at c is going to be the derivative of the outside function g evaluated at the inside function f of c. So that's g prime evaluated at f of c times the derivative of the inside function evaluated at c. So g prime at f of c times f prime of c. So in other words, the derivative of a composition is a product of derivatives. Before we see examples, I'm going to have sort of a strange discussion about how to prove this. I'm not going to do the correct proof in this lecture. So if you go to Moodle, beneath this, you'll see just an optional supplement where I go through the full correct proof of the chain rule. Instead, I'm going to give you actually an incorrect proof that seems right at first glance. It's not quite right, but it's not a bad way to think about it either. So this argument I'm about to write down has some issues. I'll say what the major issue is, which get cleaned up in the correct proof. Okay, but let's just imagine that we're trying to prove the chain rule for the first time and we're just brainstorming. So what would we do? Okay, so let's write down an expression that intuitively feels like it should give us the derivative of the composition g of f at c. I'm not going to take a limit here, partly to save room. So let me say that this is approximately a change in outputs over a change in inputs, where we'll write down the difference quotient, but without a limit. So the change in output would be g of f of c plus h minus g of f of c all over c plus h minus c. So all over h. This is definitely the correct thing to write down. This is rise over run. If we could evaluate this limit as h goes to 0, that would be the derivative. The catch is, how do you actually evaluate this? To do it correctly, see the optional supplement. But again, if we're just brainstorming, what you might think to do is multiply the numerator and denominator by the quantity f of c plus h minus f of c all over f of c plus h minus f of c. So we're not changing anything. And then the reason why this seems good is because f of c plus h minus f of c is the numerator you would have in the difference quotient for f. We want to see an f prime of c emerge out of this calculation. Next, let's swap denominators. So I've got the two fractions I need. Let me swap the denominators. We have the same numerator as before, but now all over f of c plus h minus f of c, and then times f of c plus h minus f of c all over h. This second fraction is good. This is exactly the difference quotient that we would want to see if we were trying to compute f prime at c. The first one looks good. If the inputs are f of c plus h and f of c, it's a rise over run. It's a change in outputs with respect to g over a change in inputs. But it's not really a proper difference quotient. The issue here, and it's hard to see this, but it's not a proper difference quotient. The issue here is that f of c plus h minus f of c could be 0. And that doesn't happen when h is non-zero in a difference quotient. For an example of how this could be dangerous, if f were actually just a basic constant function, the denominator would always be 0. So we could have some real problems if we tried to compute this quotient. Okay, so this is not the correct proof, but it's kind of a nice way to break it down so that you sort of see how the derivative of g comes out in the first term, and then you can see the derivative of f come out of the second term. The full proof basically just resolves this issue of having the denominator be 0. Let's work through a couple examples of the chain rule. First, let's compute the number y prime at 4 for the function y equals the square root of x squared plus 2x. This is a composition. I think it's helpful when you're beginning with the chain rule to identify the outside and the inside functions. So the outermost is the function g of x equals the square root of x. I don't want to write this as a composition. I just want to see what the outer operation is, which is that square root operation. So g prime of x is the derivative of x to the 1/2 power. By the power rule, that's 1/2 x to the negative 1/2, or in other words, 1 over 2 times the square root of x. The inside function is that polynomial f of x equals x squared plus 2x. That function is easy to differentiate using the power rule, etc., so the derivative is 2x plus 2. Now we can apply the chain rule to say that dy dx is the derivative of the outside function where we plug into that the inside function times the derivative of the inside function. So g prime of x is 1 over 2 times the square root of x, but I want to plug into this f of x. So our first term will be 1 over 2 times the square root of x squared plus 2x, because that's the inside function. And then to that, we multiply the derivative of the inside function, which is 2x plus 2. You can simplify that if you like, so that would be 2x plus 2 over 2 times the square root of x squared plus 2x, or in other words, x plus 1 over the square root of x squared plus 2x. This is actually the general statement for dy dx. If we're just interested in y prime at 4, we plug in 4, and we get y prime at 4 is 4 plus 1 over the square root of 16 plus 8, which simplifies down to 5 over 2 times the square root of 6. Now let's just compute the general form dy dx for the function y equals the quantity x cubed plus 2x all raised to the 5th power. Again, I'm going to begin by identifying the outside operation and the inside operation. So the outside function is this notion of taking something to the 5th power. So the outside function is g of x equals x to the 5th. The inside function is f of x equals x cubed plus 2x. From the power rule, we know that g prime of x is 5x to the 4th. Also from the power rule, since f of x is a polynomial, the derivative f prime of x is 3x squared plus 2. So now dy dx is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. So that's going to be 5 times the quantity x cubed plus 2x to the 4th power times 3x squared plus 2. Okay, now I would like to build up our repertoire of functions that we know how to differentiate. Thus far, we've mostly been working with polynomials or other functions where we can write the individual components as powers to use the power rule. I think the easiest function to differentiate is y equals e to the x, and this is based on the definition of e. So we gave a definition of e that was based on continuously compounding interest, but e also can be thought of as the number that satisfies the following limit. If you pick e as your base of an exponential function, then the limit as h goes to 0 of that base to the h minus 1 over h goes to 1. That actually tells you that the derivative of e to the x at x equals 0 is 1. So the slope of the tangent line there makes a nice 45-degree angle with the x-axis. This also gives us a way to differentiate e to the x at any other point x. So if y equals e to the x, what is y prime? Well, it's going to be the limit as h goes to 0 of e to the x plus h minus e to the x over h. And then I can factor out e to the x and write this as the limit as h goes to 0 of e to the x times e to the h minus 1 all over h. Pull the e to the x in front, and we have the limit as h goes to 0 of the quotient at the top, e to the h minus 1 over h. We can pull that e to the x out front because that has no h dependence. So in this calculation, x is a number in the domain that you fixed, and then you're just pushing yourself away from x by a little factor called h, but x is already a fixed number, so e to the x is just a number. You can pull that in front of the limit, and we get that this is going to be e to the x times 1, which is e to the x. So the nice conclusion here is that the derivative of y equals e to the x is just e to the x for all x. So this in some ways is the nicest function to differentiate. It's so nice that sometimes it's actually challenging for students because they see an exponential function and they think that the derivative is always itself. So let's look at two examples where you have to be careful, because while the derivative of e to the x is e to the x, that assumes that you're just doing e to the x. So if we're doing something like e to the 4x, we need to use the chain rule. Okay, so the outside function is the exponential function. So I'll write here, let's say I'm already using f. How about y equals e to the x? We know the derivative of that is just e to the x. But we have a composition, and the inside function is y equals 4x, whose derivative is 4. So by the chain rule, the derivative of e to the 4x is going to be the derivative of the outside function evaluated at the inside function. So that's e to the 4x times the derivative of the inside function, which is 4. So 4e to the 4x. For just a slightly bigger example, let's look at f of x equals e to the polynomial x cubed plus 5x squared minus 10x. Again, the outside function is y equals e to the x, whereas the inside function is y equals x cubed plus 5x squared minus 10x. So by the chain rule, df dx is going to be e to the inside function, so e to the x cubed plus 5x squared minus 10x times the derivative of the inside function, which is going to be 3x squared plus 10x minus 10. Having differentiated e to the x, it now makes sense to think about the derivative of its inverse function, natural log of x. Okay, so imagine y equals the natural log of x, and I would like to compute dy dx. We could try to set up a difference quotient and take a limit, but instead of staying in the form y equals natural log of x and working with the difference quotient, I'm going to exponentiate both sides so that we can work with e to the y equals e to the natural log of x, or in other words, x. Here, x is greater than 0. Okay, so I've rearranged terms so that e to the y is x. Now I'm going to differentiate both sides of this equation with respect to x. This is a bit strange because y is not isolated anymore. Instead, y is kind of embedded in the left-hand side. So when you look at the left-hand side, it might be tempting to say, oh, the derivative of e to the y is e to the y based on the previous slide, but that's not correct because we are differentiating with respect to the independent variable. X is the independent variable that we're going to differentiate with respect to, and y is a function of x. So we have to keep in mind that the left-hand side is e to the y of x, which is composition. So it's e to the y of x. The outside function is e to the, and the inside function is y of x. So for the left-hand side, we need the chain rule. Okay, I'm going to do this one side at a time. So let's take the derivative of e to the y. Again, the outside function is e to the x. We know the derivative of e to the x is just e to the x, so the derivative of the outside function is the outside function. The inside function is y of x. The derivative of y of x is just dy dx. That's how we'll denote it. Therefore, using the chain rule, the derivative of e to the y is e to the y times dy dx. The right-hand side is easy. That's just x. d dx of x is 1. So now we equate both sides and we can say that e to the y dy dx equals 1. dy dx is what we're looking for. That's the derivative of y equals natural log of x. We're trying to find the derivative of natural log. So I could isolate that and say that dy dx is 1 over e to the y, but that's a little strange because it's not in terms of x. Keep in mind though, e to the y is x. That's actually the new equation that we brought into this calculation. So I can replace e to the y on the left-hand side and get x dy dx equals 1. This tells us that the derivative of natural log of x is 1 over x. It's always nice to kind of step back after computing a derivative, if it's a nice function that you recognize, and think what this says about the slope of the tangent line. Notice as x goes to 0 from the right, 1 over x is going to grow to infinity. And that makes sense because natural log is very steep as we approach the y-axis from the right. Right, so the y-axis is a vertical asymptote for this function. On the other hand, while natural log of x does grow to infinity as x grows to infinity, it does so very slowly. This function turns really flat. And we see that in our derivative calculation because 1 over x as x goes to infinity is going to head towards 0. So the derivative is always positive. We always have a tangent line with a positive slope, but it gets flatter and flatter as x grows to infinity. So this derivative agrees with our understanding of what the natural log function looks like. At this point, we've gone over every major technique of differentiation that we're going to see. So given two functions, you can add them together, and we know that the derivative of the sum is the sum of the derivatives, etc. And then we also saw composition with the chain rule, and that's a really key one because we can compose multiple functions. So we phrase the chain rule as a composition of two functions, an outside function evaluated at an inside function. But you could have several nested functions, and in this case, you would just apply the chain rule carefully. So let me give you an example, which we can now differentiate. We would like to find the derivative of e to the x squared plus the square root of x cubed plus 1. Okay, I would really say that this is perhaps 3 functions nested. The outermost is the exponential function. So the outside function is this action of e to the x. We know the derivative of e to the x is just e to the x itself. At first glance, the inside function is y equals x squared plus the square root of x cubed plus 1. So now I just need to know the derivative of this function. From the power rule, the first piece is 2x plus, but now I need to take the derivative of the square root of x cubed plus 1, and that's composition in its own right. So looking at this, the outside function is the square root function. So my outside function I could describe as y equals the square root of x, or to apply the power rule, it might be easier to write that as x to the 1/2 power. Then I know that y prime is 1/2 x to the negative 1/2, or 1 over twice the square root of x. The inside function is a polynomial y equals x cubed plus 1, so its derivative is 3x squared plus 0. So the derivative of e to the x squared plus the square root of x cubed plus 1 is going to be the derivative of the outside function evaluated at the inside function. So that's e to the x squared plus the square root of x cubed plus 1 times the derivative of the inside function. So that's the derivative of x squared plus the square root of x cubed plus 1. But now to take that derivative, I'm going to do the chain rule again. So the derivative of that inside function is 2x plus the derivative of the outside, so 1 over twice the square root of the input, where the input is x cubed plus 1. And then times the derivative of the innermost function, so the derivative there would be 3x squared. And now you can just simplify as much as you like. So this is going to be e to the x squared plus the square root of x cubed plus 1 times 2x plus 3x squared over 2 times the square root of x cubed plus 1. So you can see you can have several levels here. So we could even have kept going if we had multiple nested functions. So the chain rule is pretty powerful. Okay, so that's it for this lecture. We've seen now how to differentiate any kind of polynomial. We can also compute the derivative of rational functions using our ability to compute the derivatives of polynomials together with the quotient rule. how to differentiate e to the x and natural log of x, and then when we already know how to compute derivatives of given functions, how to combine those functions. What's missing here is really trig functions. So I've put some trig function derivatives on the homework. And then once you've kind of worked through all of the major building block derivatives, you want to have like a chart that you know. So if you see x cubed plus e to the x, you immediately know that that derivative is 3x squared plus e to the x. All right, but that's it for this lecture. Thanks for your attention.